Okay. So, how this is coming? I am writing one line for you, that this equation we have taken no 2B equation, delta V is equal to your Z bus, that is CF, right. So, delta V actually what? Delta V1, delta V2, then delta VR say rth bus, then delta Vn, right, and is equal to, this is Z bus. So, Z11, Z12, then Z1n, then Z21, Z22, Z2n, right. If you come to rth bus, so it will be ZR1, ZR2, somewhere that element ZRR will come, then ZRn, right, and then your last one, that Zn1, Zn2, then Zn, right, and this fault current CF all are zeros except that rth bus IR is equal to, we have taken that your what you call IRF is equal to minus IF, right, and all are zeros, all are zeros. So, when you take this your delta VR, all will be this thing, only delta VR will become your this is minus IF. So, minus ZRR into IF, right. That is why you are writing delta VR is equal to minus ZRR into IF. This is equation 5, right. So, now that means that that means this just hold on, that means the voltage at the rth bus under fault, that is VR0 VRF rather, VRF is equal to pre-fault voltage VR0 plus delta VR, whatever changes ground, right, is equal to VR0 minus ZRR IF. This is equation 6, right. Also VRF is equal to ZF into IF from this diagram, right. From this diagram, right, your if you write from this diagram that VRF, that fault current is IF and this is ZF. So, VRF will be ZF into your this thing, what you call IF, right. So, that is why you are writing ZF into IF from this diagram only, from here only, right. That means your then equation 6 and 7, but VRF is equal to VR0 minus ZRR IF. Therefore, this VRF, that is ZF IF is equal to VR0 minus ZRR IF, right. That means your this come to next page, that means your from this equation only you can get that IF is equal to VR0 upon ZRR plus ZF, right. This is equation 8. Now, using equation 5 at the ith bus, when R is equal to I, at equation 5 we put, look, that equation was given delta VR is equal to minus ZRR IF, but at the ith bus put R is equal to I, don't, it is given Z, your delta Vi is equal to your minus your ZRR IF, but please do not put both the, you do not replace both I by R or R by I. So, only R is equal to I. So, that equation will become delta Vi is equal to minus ZIR, right. Do not make ZII, then it will be mistake, minus ZIR into IF. This is equation 9, right. Therefore, equation 6, using equation 6 at ith bus when R is equal, in equation 6 you put R is equal to I, right. That means, in this equation you put R is equal to I, right. So, in that case your VIF will become VI0 minus ZIR into IF. This is equation 10, right. That means, from equation 10 and 8, right, from equation 10 and 8, that IF is equal to VR0 upon ZRR plus ZF, this one you substitute here, this one you substitute here. If you do so, then you will get your VIF is equal to VI0 minus ZIR upon ZRR plus ZF into VR0. This is equation 11, and in equation 11 you for I is equal to R, when I is equal to R you put it here. Therefore, you will get VRF is equal to VR0 minus ZRR upon ZRR plus ZF into VR0, or simplifying this one, VRF is equal to ZF upon ZRR plus ZF into VR0. this is equation 12, right. So, these are all your all this fault calculation for a large network, right. So, this thing, that means you note that Vi zeros, right, are pre-fault bus voltages and can be obtained from the load flow studies, and Z bus matrix for short circuit study can be obtained by inverting Y bus matrix, right. Also note that synchronous motor also must be included in the Z bus formulation for the short circuit studies, right, if it is there. However, in formulating short circuit study network, right, your short circuit study, the load impedances are ignored, because these are very much larger than the impedances of the generator and transmission lines, right. So, that load impedances are ignored, right. So, these are what you call that this is a general thing, that you have a power network, fault has occurred at a particular bus bar, and that all the generators EMFs are short circuited by their your whatever you require by their reactances, transient or subtransient, right, and for fault the bus where fault has occurred, right. So, you have to get a Thevenin equivalent. So, you excite that one by a by pre-fault, that is pre-fault voltage is there minus VR0 in series with that your fault impedance, right, and accordingly all other calculations are same. That means, all that equivalent network, that your current injection at the faulted bus will be there, that is minus IF, or the rest of the buses there is no current, all current injection is 0. Based on that we got this one, right. That means this fault current flowing from bus I to bus Ij, that is If Ij is equal to Yij Vif minus Vj. If you know Vif, if you know Vjf, then you can easily calculate, and post fault generator current for ith generator in general If Gi Vgi dash minus Vif upon Jxgi dash. This is equation 14, right. So, this way we can, this way you can go for your what you call that Thevenin equivalent, and accordingly you can compute all the fault voltages and the current, right. Now, before going to the Z bus algorithm, we will take one example. For example, this one your what, this is a network, transformer is there, is reactance is given, generator is there, Xg1 dash is given, here also same rating 11 kV 100 MVA, right. The transformer reactance is given 0.05, generator is given X2 0.10, these are all the line impedances are given, resistance is neglected, and fault has occurred at bus 4, right. So, assuming pre-fault bus voltage all are 1 and pre-fault currents are 0, right. So, this assumption we have to make, and you have to find out your what you call that your short circuit solution. All these things you have to get. First thing is you have to obtain the Y bus. So, in this case this you have to obtain the Y bus. In this case what will happen, we will compute the Y bus, that suppose Y11, it will be Y13, it will be Y12, it will be Y14 plus that your another thing, if you make some bus number Y10, some bus number 0. So, this generator Xg1 dash and transformer T1, this also you have to consider, right. That means, you have to consider that 0.05 and 0.11 here, they are in your what you call series. So, 0.15, that means your what you take, this is impedance is given. So, you have to find out Y13, Y12, Y14 plus say Y10, right. That means, this 0.1 and 0.05, with that you construct the Y bus matrix, right. Well, after constructing the Y bus matrix, this matrix I have with me, but I am not giving you this matrix, you construct and you will get Z bus is equal to Y bus inverse. This is actually all Z's are given, this will given. Now, question is our interest is to get the Z bus matrix, right. So, in this case what will happen, that Z bus actually it is a 4 bus problem, it is a 4 bus problem. So, Z bus will be a 4 into 4 matrix, remember, note that. that classroom we cannot do 4 into 4 matrix inversion from y bus, it is not possible in the classroom, we need computer. So, whenever we are giving numericals or problem, this data will be provided, right. So, whatever z bus will come, the directly data will be provided, right. Otherwise, one cannot solve the problem in the classroom, but when we take that, you construct the y bus and if you take the inverse, right, and for example, you convert y bus, then in MATLAB it is a 4 into 4 matrix. So, y bus inversion you will get it, it will not give any error, right, and this is actually your z bus, it is a full matrix, it is a z bus, right. So, z 11, z 12, this is z bus. So, that means from here you all the z elements will get for z 11, z 12 everything, and it is a symmetric matrix, right. So, using equation 11, that VIF is equal to VI 0 minus ZIR upon ZRR plus ZF into VR 0, right. So, now your all pre-fault condition, your just hold on, all pre-fault condition, right, your V1 is V1 0, V2 0, V3 0, V4 0, they all are 1 per unit, and bus 4 is faulted, that is R is equal to 4, that Rth bus is a faulted bus, that with fault impedance ZF is 0, because it is a solid fault we have taken. So, V1f is equal to V10 minus Z14 by Z44 into V40. That means, this equation in this equation you put I is equal to 1, 2, 3, 4, right. Then you will get V1f is equal to whatever you substitute all these value, whatever will come 0.4247 per unit. Similarly, V2f you will get V20 minus Z24 by Z44 into V0, whatever it comes you will get 0.4697 per unit, right. Similarly, your V3f you also will get this V30 minus this one, you will get 0.4520, and fault has occurred at bus 4. So, V4f will be 0, right. So, V1f, V2f, V3f, V4f you have got. Now, fault current can be computed using equation 1-3, IF ij, Yij, your Vij minus your Vjf, right. So, Y12 actually is equal to 1 upon Z, because now we are actually do not take capital Y, this thing Y matrix, it is a small y, because you only line fault your line fault current you are computing. So, I is equal to 1, J is equal to 2, IF12, Y12, V1f minus V2f, that is 1 upon your Z12, right, into V1f minus V2f. You will get IF12 is J 0.1125 per unit. So, this is a small y and Z is given. So, Y12 is 1 upon Z12, accordingly you calculate. Similarly, for all other things, for IF13 you will compute, right, then IF14 again you will compute, IF24 you will compute, IF23 will compute, right. So, this is actually that is simple example, that using that your what you call that Thevenin equivalent, right, easily you can compute your what you call that all the fault currents, right. But only thing is that you have to have that Z bus matrix. In fault studies Z bus matrix is necessary, right. So, up to this actually intention of this chapter is to show you couple of example of this fault studies, and main thing is that your Z bus building algorithm, that how one can make that Z bus building algorithm rather than taking your Y bus inverse, because the Y bus inverse if it is for a large network, right, computationally may not be that this thing, you have to go for a different algorithm. Direct inverse if you take direct inverse for large system it may give error. So, some special technique is there, but for getting inversion, but we will not discuss that, but our object is now to formulation of Z bus matrix, right. So, this 3-phase symmetrical fault, as I told you that it is very rare, but still we have to study this one, right. So, detailed symmetrical component and that positive, negative and zero sequence component at the time unbalanced fault detail we will see, and we will take different type of examples. Now, formulation of Z bus matrix. So, basically I bus is equal to Y bus V bus, I am writing it is C bus is equal to Y bus V bus. C actually current, C stands for current, is equal to Y bus V bus, right. This is the formulation of your Z bus matrix. Now, this V bus then is equal to Y bus inverse C bus, that is equal to V is equal to Z bus I bus. Actually, I bus, instead of I bus I am taking C bus, right. So, this is equation 15, where Z bus is equal to Y bus inverse. Now, Z bus formulation by current injection technique, although this technique is not good enough, but just see how things are, right. So, this equation 15, I mean this equation, if you write them in I mean all the equations rather than matrix form in all the equation, then V 1 you can write Z 11 I 1 plus Z 12 I 2 plus Z 1 n I n, right. Similarly, V 2 is equal to Z 21 I 1 plus Z 22 I 2 up to Z 2 n I n. This is equation 17, right. I mean set of equation, of course, V n is there. So, Z n 1 I 1 plus Z n 2 I 2 plus Z n, this set of equation we are making, that is equation 17, right. So, in equation, that means this equation 17, that if we want to compute Z 11 Z 12, right, then we can write that Z I j, you can write Z I j is equal to V I upon I j, when I 1 is equal to I 2 for all I n 0, but I j not is equal to 0, then you will get Z I j. This way you can obtain. Now, so in this case we will take one small example, right. Suppose you have a simple your bus 1, bus 2 and one reference bus is there. So, this is V 1 voltage, this arrow means it is plus polarity and here it is minus, right. Here same thing for V 2. So, a current is here showing I 1, here it is I 2, and this is something, some resistive is showing 4, 5 and 6, right. You can take per unit only, right, and this is reference bus. So, you have to obtain the Z bus matrix for this system, that V 1 is that is and V 2, that is the voltage of that bus 1, bus 2, right, with respect to this reference bus, and these are that branch element 4, 5, 6 we have taken. Now, what you can do is to get this your impedance of this one, impedance matrix of this one. For example, that first what you do at bus 1, keeping your bus 2 open, bus 2 is open circuited, right, and at bus 1 you inject 1 per unit current, right, you just inject 1 per unit current at bus 1, but bus 2 is open circuited, right. That means, this I 1 1 per unit current, it will, and this as nothing is injected here. So, current here from this bus to basically I 2 is equal to 0, right, and I 1 is equal to 1. So, this I 1 current is flowing here, then as this current is 0, same I 1 is flowing here, right, and this way it is return path, right, this way returning. Now, in this case what we will do, so I 1 is equal to 1, I 2 is equal to 0, what you do first, that you apply first your KVL in this equation first, in this equation first, sorry, in this loop first, apply KVL. If you do so, it will be I 1 into 5, right, plus your I 1 into 6, right, is equal to V 1, because this voltage here it is V 1, right. So, I 1 into 5 plus I 1 into 6 is equal to V 1, that means V 1 by I 1 is equal to 11. So, V 1 I 1 is equal to nothing but Z 11. So, Z 11 is equal to 11, right. Similarly, in this loop you apply KVL in this loop. So, I 2 is 0, 0 into 4 0 plus I 1 into 6 is equal to V 2, right. So, this I have written in the your next page. That means, Z 11 is equal to, we got it 11, right, V 1 upon I 1 is 1 per unit. So, directly writing this one, and in the second case it is 0, I 2 is 0, 0 into 4 plus I into 6, sorry, I 1 into 6 is equal to V 2, V 2 by I 1, that is equal to Z 21. So, Z 21 is actually is equal to 6, because I 1 is 1, that means Z 21 is equal to V 2, that is equal to 6, right. Similarly, keep this one open, right, and at bus 2 you inject 1 per unit current, right, and same way you apply KVL once in this loop and apply KVL in this loop. You will get Z 22 is equal to V 2 upon I 2, because I 2 is 1 per unit, you will get 1 per your 10, and similarly Z 12 you will get V 1 by I 2, that is equal to 6. Once in this loop you put KVL, another one here you put KVL, everything is given, right. That means Z 1 1, Z 1 2, Z 2 1, Z 2 2, you have got it, right. So, Z bus, this is a current injection method. So, Z bus is equal to Z 1 1, Z 1 2, Z 2 1, Z 2 2 is equal to 11 6, 6 10. This is the Z bus matrix, also referred to as the open circuit impedance matrix. So, this is one methodology I showed you that one can obtain that your this thing, but for large network this is actually getting Z bus is a difficult one, right, for this way. So, now algorithm for building Z bus matrix. So, Z bus matrix actually is a step by step procedure which proceed branch by branch, right. So, you have to move branch by branch, and this one, right, you have to we have to try to understand this, that how to go for algorithm for Z bus building algorithm. But let me tell you, as far as coding is concerned, this quite easy. Those who knows coding and interested about all these things, in coding actually is easy. So, main advantage of this method is that any modification of the network element does not require complete rebuilding of Z bus matrix, right. That means, if some modification is there in the network, right. So, this using this algorithm, whole network no need to modify, only certain portion you have to, wherever you need, that there you have to modify. But if you go for inversion of Y bus matrix, then even a small modification also you need the whole inverse thing, right, which is not desirable. So, that is why you will go for Z bus building algorithm. So, first is some kind they say that type 1 modification, right. So, type 1 modification means that what is some type 1, type 2, type 3, type 4, this way we name it. So, in this case I will explain it, I will show the figure that branch impedance ZB is added from a new bus to the reference bus. We will consider some buses are new bus, some buses are old bus, right, and one reference bus. So, in this case branch impedance ZB is added from a new bus to the reference bus, that is a new bus is added to the network, and one dimension of Z bus goes the dimension of Z bus goes up by 1. That means, suppose you have a n bus problem and you are adding a new bus, means that Z matrix will dimension will increase by 1. Suppose it is a 10 bus problem, suppose Z is 10 into 10 matrix say, and you are adding one more bus 11th bus. So, Z bus will be 11 into 11 matrix, so it will go up by 1. So, what you will do it, you take a passive linear n bus power system network, right. You have bus 1, bus n, bus I, bus j, and k bus is a new bus and r is the reference bus. So, how we will proceed actually, this notation we have to understand, that bus I and j, this is old buses, right. Bus r reference bus, bus k it is a new bus, right. That means a new bus is added to the network, right. So, that means this is a k bus is a new bus and it is added to a, it is connected to a reference bus, right. That means, this is the type 1 modification, that branch type 1 modification, that branch impedance ZB is added from a new bus to the reference bus. That means, this is a k bus is a new bus, I have written there, this notation very important, that k is new bus, it is added to through an impedance ZB. Therefore, voltage with respect to reference bus here, kth bus voltage is Vk and current is Ik, right. This current injection at this bus k bus is Ik. So, if it is so, that means you can say that Vk is equal to Ik into Zb, this is directly you can write Vk is equal to Ik into Zb, right. Or, so from figure 6, from this figure only, that Vk is equal to Zb into Ik, that is your Vk is equal to, instead of Zb, it is a branch impedance added, we can write Vk is equal to Zkk into Ik, because Vk Ik is here. So, better notation should be Zkk, but as k is not connected anywhere, right, you better you make Zki is equal to Zk is 0 for I is equal to 1 to n. So, all other z's are 0, you need not consider actually the mathematical equation. That means, Zkk actually is equal to Zb, and order has bus your Z matrix order has increased 1. So, Z bus new will be whatever Z bus was there, it was there, all, and but dimension is increased by 1. So, all this row up to this it is 0, up to this is 0, only diagonal will be ZB, that is your ZKK, right. That means, this is because this is Vk is equal to ZKK. So, kth bus is added. So, that is why dimension is increased by 1, and this Z bus old was available to you for the system. How we are doing it later we will know, right. So, this is equation 9, this is called type 1 modification. So, simple one, the first one, right. Only one element will be added to the diagonal of the old Z bus. So, and these are all zeros, this row, this column up to this, and this row up to this, all elements will be 0, right. Next is that your type 2 modification. So, previous one Z bus old is the bus impedance matrix before adding a new branch, that I told. Now, type 2 modification, in this case what will happen, that branch impedance ZB is added from a new bus K to the old bus J. So, I have told you that our bus I and J, they are old buses, right, and K is a new bus and R is a reference bus. So, in this case branch impedance, there is a type 2 modification, that branch impedance ZB is added from a new bus, this is a new bus, to that your old bus say J. That means, this bus is added through impedance ZB, this current is IK, this is IJ. So, current injection here is IJ plus IK, and this voltage here the Z bus voltage is Vj and kth bus voltage is Vk, right. So, that means, from this figure, in this case you apply KVL. So, it will be IK into ZB plus Vj minus Vk is equal to 0, that means Vk is equal to Vj plus ZB IK. This way I have drawn for you, such that it will be easy to understand, right. So, now this Vk is equal to Vj plus ZB IK, that means we can write, right, we can write, this is your this equation, that as a whole we can write V1 V2 Vn, right, and this is Z bus old, right, and this is your this ZJ1 ZJ2 Zn, and here how it is coming we will see, and this is your current IK. So, if you see that Vk is equal to, it is Vj plus ZB IK, right. So, Vk is equal to, that means I am coming here, that Vk is equal to, it is Vj plus ZB IK, that means Vk is equal to ZJ1 I1 plus ZJ2 I2 up to plus ZJJ Ij, that is Vj, right, plus Zjn In, now plus ZB Ik, right. So, this thing actually ZJJ plus your this thing, if I go to the first equation, ZJ1 I1 plus ZJ2 I2 plus ZJJ Ij plus Ik, because here current injection is Ij plus Ik. So, ZJJ Ij plus Ik plus dot 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 Zjn In and plus ZB Ik, because in this equation where it has gone, in this equation Vk is equal to Vj plus ZB Ik. So, first we have written Vj up to this, the red color, plus ZB Ik. After that, if you simplify, it will come plus ZJJ plus ZB Ik. That means, this equation Z bus new, Z bus old will be there, and this last one Vkth one, it will be Zj1, Zj2, Zjn. It is symmetric matrix. It is Zj1 means Z1j, Zj2 means Z2j, Znj, and this diagonal, last diagonal one Zjj plus Zb. This is Zjj plus Zb, right. That is why I was writing this one. Just hold on. This your what you call this Z bus new is equal to this one, right. So, this is actually your Z bus new, Z bus old. So, only from this equation only Vkth equation will be added, right, and then you simplify. So, in this case also dimension of the Z bus matrix will increase by 1, because it is k bus is earlier it was added to reference bus, now added to an old bus. So, only this element one has to compute, right. Particularly this one, other things are known, but it has increased by this one, right. So, this is actually Z bus new. So, thank you, again we will be coming back.